Welcome back, everybody, to this lecture on convolutional neural networks. That's going to be the main part of the lecture today, and then we see how far we get. And if we get far enough, we may jump into recurrent neural networks, or we may just postpone that topic to next week. So last week, we went through the mathematics, the basic mathematical operations of a convolutional neural network. So I'm going to set up and repeat some of the basic steps, and then we are going to dive into how we can write codes. And many of you will most likely use TensorFlow with Keras as an interface. So Keras is an API which links with TensorFlow, or you may prefer to write your codes with PyTorch. Now, for the all these kind of applications and implementations, you will find examples both in the textbook by Rashka, and in Rashka you have in chapter 14, which is dedicated to convolutional neural networks and how to set it up with PyTorch. There is a simple example which I have placed in the lecture notes here on PyTorch. And then for recurrent neural networks, there is a similar chapter in Rashka's text, chapter 15. So these are very useful chapters. And as you know, you can download this book for free from the university library. Secondly, if you want to read more about the theory for CNNs and RNNs, we have good fellows as an excellent introduction to the methods. So last week, we looked at the way we do convolution and the mathematics of it. So today, we're simply going to look at how do we implement these different operations. But let me quickly remind you of some of these features which we have for CNNs in brief. So if you look at the images here, so a CNN architecture contains of what we last week called a so-called convolution stage. And that convolution stage includes, as you can see from the image here, a production through applying different filters of a given number of replicas which have been downsized. And these downsized replicas, you can decide how many you want to have. So like in this example here, you can have a filter which is given by 5 by 5. And when we are going to look at the TensorFlow implementations, there are some features in TensorFlow which are very nice to use, which is called model summary, which we will see a little bit later. And that allows you to count the number of parameters you have to fit. So the typical way you would proceed would be, for instance, one convolution stage here. And then you have what we call pooling, which I will repeat soon, what it actually means. So 2 by 2 means that of an image which is 28 times 28, you split sub-blocks, which are 2 by 2. So if you have a 28 by 28 matrix, think of you splitting this in sub-blocks of 2 by 2. And then, so that means that you have 4 values. And then you can, if you use max pooling, you can pick the largest values of these 4, or you can take the average. These are the standard ways of doing this pooling. So this convolutional stage also includes what's normally called a ReLU stage, where you can do some further downsizing of the image. But you see here now, by this 5 by 5 filter, you haven't actually downsized the image much. You kept the same size. And then you can do some pooling, and then you reduce it by 14 by 14. And then you can do a new convolutional stage, and then a new pooling stage. So you end up with an image which is a 7 by 7. And then you have made 64 replicas. So the kind of idea is that these filters act on different parts of the image, and you keep this information, and this information has been downscaled. Now, the filtering itself is an art, which is something when you're applying convolutional networks, what I would typically recommend is to look at what people have done before, because there's a lot of hand tuning with respect to the type of data which you have to deal with. So as I mentioned last week, a typical example, which is very simple to understand, is the case of you recognizing buildings. And when you do buildings, you would typically keep track of where the windows are, the corners, the roof, etc. But you wouldn't store all the information about the wall and the color on the wall, which most likely is the same throughout the wall. So that means that when you scale your image down, you would focus on some specific feature. So that would be a very tailor-made type of filter. And this is something which you would often do when you have some specific applications. And then there is this flattening stage where you just flatten your data, and then you feed that one into a standard feed-forward neural network. And in this case, what you see here is an output where you have only 10 classes. So this would be a typical example of a classification problem. And if you're thinking of this MNIST data with 10 handwritten numbers from 0 to 9, then you would have 10 classes. So your final output is an output layer with 10 nodes, which is then driven by the activation function, which we normally call the softmax function. So these are typical applications, and you can make these networks deeper and deeper. So that means that you can have many such convolutional stages. Now, when we come to these implementations with TensorFlow, etc., you will see how you can actually set up the filters and the type of pooling layers, etc., and see how many parameters. So the basic idea, if you think back of a neural network, which is represented by affine operations, so in a neural network, you keep all the nodes and information of the weights and biases. So there is no downsizing of this matrix which you're looking at. So you can think of CNN as a way to perform a dimensionality reduction, which then allows you to perform these affine operations in the standard neural network stage. So that means that the matrices which you deal with are matrices which you can easily run through a standard feed-forward neural network. So that's the kind of basic idea here. So then I wanted to actually remind you of something which you probably have not seen before, but it's a kind of reminder about the singular value decomposition. So I'm not going to go through the mathematics of the SVD now, because we will discuss that in connection with autoencoders. But the singular value decomposition is an algorithm from linear algebra, which allows you to decompose the matrix which you have in terms of two orthogonal matrices, and a matrix which is diagonal, which contains the so-called singular values. So a matrix which you cannot invert, which is a singular matrix, can always be decomposed in terms of a singular value decomposition, or the SVD. So the old approach to this was actually to take your image represented by a matrix, and then you could scale it down. So when you perform a singular value decomposition, suppose of 100 times 100 matrix, a square matrix, that gives you 100 orthogonal vectors in the transformation. This information encodes your matrix. So you can keep all 100 vectors, or you can keep only those which have the largest eigenvalues. So that's a way to downsize the image. So there's somebody who came online here with a lot of noise. Okay. A lot of noise in the background here, so somebody. Oops. So for those of you online, I may actually switch. There was a huge amount of noise here in my AirPods. No. Things gone wrong here, but for those of you online, can you hear me when I speak here now?
Yes.
Yes.
Okay. Okay. So I'm gonna stay close to my laptop because that has the microphone, which is a microphone which is weak. So if I move away from my laptop, you will probably not hear me well. So I'm gonna see if I can fix my AirPods here during the break. Now, the singular value decomposition then, when you perform a decomposition on a matrix, you will then get a representation in terms of orthogonal vectors, and you can decide to keep those vectors which represent the largest eigenvalues or the singular values. If you do that, that is a way to compress your matrix to, let's say, you keeping only 5 of the vectors, of the orthogonal vectors. And this was a technique which was widely used. And then but you need to keep the information about the transformation, the mapping from the original size to the smaller size, because sometimes you want to reconstruct the image. So in this specific case, what I've done is actually to use the singular value decomposition and make a compression of a matrix where now I have a matrix of an original size of 800 times 1200. And I'm going to reconstruct it in terms of different compressions where I keep different vectors here. So I can keep only 5 vectors, 10, 20. So these are the vectors which have the largest eigenvalues. We are going to or singular values. We are going to discuss this algorithm in more detail in connection with autoencoders, when we are going to show that autoencoders can be understood as a principal component analysis method when you have a linear transformation. So just bear with me now, and we are now going to look at the way we can compress a specific image. And this image is of a beautiful place in a beautiful country called Italy. And it's a city which is called Volterra, which is a Florence in miniature. And it's a city which has been settled for more than 4,000 years. And this is a full image. So if you happen to be in Tuscany, you should go to Volterra. It's a beautiful spot. Now I can keep only 5 eigenvectors, and you see the image here. It's pretty blurred, right? But you still see the buildings. So this is a way to downsize the information of an image. And then you can move on and increase, so you keep only the 10 vectors. And then you can keep increasing this. You have 20. You see now it's actually getting better and better. So which type of, how much information you want to keep, this is you who decides that. But like already here with 20 vectors only, you can actually get a pretty good reproduction. And in this case, we have downsized it to 100. And you can see when we do the downsizing here, it gives you the compression rate, which is 28%. And there's still a mean square deviation from the original image, which is 70, so it's pretty large. But even in this case here, you can now see that you recognize, you can even read on this wall here, which is actually the Sparkasse or Sparkassen in Norwegian. Kasse di risparmio. And then you can keep going. And you see it becomes sharper and sharper. And then I went up to 300. And finally, I did 400 here. And this is almost close to the original image. So you can actually downsize. And this was the way this kind of storage of images, where you would downsize them, was done previously, before people started with convolutional neural networks and deep learning methods. So this has been a traditional technique in filtering. So if we now go to one of the things we discussed last time about pooling, and let's do that and remind ourselves of that before we move on to the way we would encode the information ourselves. So pooling is one of the ways by which we reduce the dimensionality. And the typical way, if you have now a 2x2 filter, so here we have a stride of 3, as we discussed last time. So your image now has been reduced, or you have made a copy of your image. And in this case here, you have a 6x6 matrix. And suppose now the values look like this. So you can do max pooling. So that means that you take the largest value among this 3 by 3. So this pooling is 3 by 3. You will see in the examples typical pooling cases like 2 by 2. And 3 by 3 are typical pooling filters or downsizings, which you would do. So what you see now is that your original object, which is a 6 by 6 matrix with a 3 by 3 pooling, is then reduced to a 2 by 2 matrix. So it's a way to keep the most important information about a specific image and then reduce the dimensionality. Another way of doing that is something which is called mean pooling, where you simply take the average value of all these entries. So these are the standard ways which are used in order to reduce further the dimensionality of the image. So if you go back to the image which we had here, this pooling here is a 2 by 2 pooling. And that means obviously when you have a 28 by 28, you reduce that to a 14 by 14. And then you made 32 replicas. So when you use a software like TensorFlow, the TensorFlow is actually together with Keras, which is an application, an API, you can then easily set up a convolutional neural network. And the type of data which we're going to look at is this MNIST data. So I'm going to use that, and I hope it's not too boring, but that's a kind of benchmark data which is used in essentially all machine learning texts. This is a data set which now contains something like, I think it's close to 60, 70,000 images of dimensionality 28 pixels times 28. And these are black and white images. So if you then think of a standard feed-forward neural network, it means that a node from the input layer would then connect to a node or the nodes from the input layer. You would have 724 nodes. And then each neuron in the first hidden layer would then be connected to 724 neurons in the input layer. And that gives you 724 weights. So if you have 100 neurons, that means that your matrix would be 724 times 100 with weights to be determined. So that would be a typical dimensionality if you run this as a standard affine transformation with a neural network. So when we now look at these layers here, so I'm just going to jump into the way you would use TensorFlow. So we use that with Keras, which makes life much, much easier. We import given data sets. We need to have an input layer. This is a sequential model because it runs sequentially. Everything we do is actually set up in a sequential order. So a feed-forward neural network is nothing but a sequential ordering of all the operations we do. We start with the input layer. We move to the first hidden layer in a sequential order till we reach the output layer. So we need to include these sequential models. We want to have dense layers. We need to have optimizers. We will normally regularize. And then we need to decide also what kind of output layer we want to deal with. And in our case, we are going to look at categories or classes. So then we need to import this two categorical here. So let's just run this one. Now, what we can do, this is an example of us doing this without a specific image. So this is just an example of how you would set it up without applying it to any type of data. So I'm just setting up this input shape. So I'm assuming that this is a color image with 32 times 32 pixels times 3 color channels. And now I'm making 32 copies of it. And I have a 3 by 3 filter. So this is the way you would specify the filter you're doing. And then I define the activation function to be ReLU. You can change that one. You can change this to GLU, ELU, rectified, linear units, etc., etc. Then there's a pooling. So that means that we do a 2 by 2 pooling operation. So that means that the original size of the matrix, which was a 32 by 32, then we have a 3 by 3 filters. That scales the image down. And when you don't say anything, padding is 0. and stride is 1. These are the default values. So if you want to add padding, you need to add that as a parameter in the setup on the convolutional layer here. So that means that you're scaling this down to a 28 times 28 image with a 3x3 filter. And then when you do this, you will get a 14x14. And then you can continue, so you can do a new convolutional operation on the data. So you can just keep repeating this type of convolutional operations. So this setup which you see here is pretty close to the first image which we looked at in the beginning of the lecture. Then we can continue. We have a new pooling layer. We can do a new convolutional layer. So these are just examples on how you can proceed. The thing which is nice is that TensorFlow comes with a function which is called summary, and that tells you how many parameters you have. So in this case here, you have reduced this now, not 28 by 28 by 30 by 30. So you have 32 replicas. You do a 2x2 pooling, so that reduces to 15 by 15. You have your 32 replicas. And then you do a new one, a 3x3, but now you want 64 copies. And now you're reducing this one to a 13 by 13, and you have 64 copies. You do a max pooling, so that gives you a 6x6. So you have reduced it further. You can do a new convolutional layer and reduce the image further. So what is nice here is that it gives you the parameters to train. So your first convolutional layer gives you in total 196 parameters of weights and biases in the filters, which you need to train by backpropagation. Then there is no parameter to train while you run the network with max pooling. That means that here you fix the pooling as a hyperparameter. So this is your architecture of the network, okay? So if we just go back again, if we remind ourselves about the images, the first image which we looked at, so let's just do that. In this image here, in the convolutional part, we have parameters to train. In the pooling part, we have decided that the pooling is given by a 2x2. So that these become hyperparameters, and you can change this and just see if you get better results. So that's part of your experimentation. Now, in the convolutional layer, the ReLU function, which is also used sometimes to reduce the dimensionality, that is also set by hyperparameters. So the ReLU function becomes a parameter in your architecture. Same as the filter here. This is a 5x5 filter. This is also a parameter which you set in the definition of the architecture. So when I say model, I also mean the architecture of the network. So these are hyperparameters which are set before you start running the calculations. So if you then scroll down here and look at the way you would implement this with TensorFlow and with Keras, this is gives you a quick summary of the parameters. And then you can add a dense layer on top of it. You have this flattening layer, which does not introduce any new parameters. But then you can have your neural network where you treat in the 64 images. And this neural network normally has something like, I think the 64 has 100 nodes by default and one hidden layer. But now you can see when you write this model summary, so this is the last layer where you have only 10 output nodes. No, sorry. I think this is 64 neurons in a one hidden layer. So you can make this neural network more advanced. You can make it deeper if you want to. This is by default just a neural network with one layer. And now you see all the parameters you need to train by backpropagation. So the output layer has obviously only 10, and that connects with the 64 neurons. So 10 times 64 is 640. And then you have 10 biases. So that gives you 650. So that's the number of parameters for the output layer. And then you trace back and you have your neural network, which now contains 60,000 plus. And then there is nothing in the flattening in this convolutional layer where you reduce your image to a 4x4 and you have 64 replicas. Then you have this amount, 36,000. And then there is nothing in the pooling layer because there you have only hyperparameters. And then you have new parameters to train here. So in total, you have something like 120,000 parameters to train in this specific model. So that's a typical example on how you would set up TensorFlow with Keras. And the thing you need to understand is simply what do these different parameters mean? So just to quickly summarize here, if you look back here, you see now that you are making 32 replicas, and then you have a filter which is 3x3. Stride is by default 1, which means that you move one column at a time. And when you've gone through all the columns, you go one row down again, and then you keep doing the mathematical process of convolution. And then you have the pooling, where you can decide how big blocks you want to do the max pooling on. And the typical sizes are 2x2 or 3x3. These are very typical pooling layers. And the typical filters are either 2x2, 3x3, or 5x5. So these are typical examples of filters which you will encounter and which you may play around with. Any questions so far? Yeah.
Is it wrong to have the stride equal to the liquid size?
Yeah, you have to be careful with the stride so it matches the size of the input data. So that's important. So the example which follows here is an example where we look at the MNIST data. And here I have the reduced MNIST data. So I'm using scikit-learn. And scikit-learn just introduces a scaled down version because that allows me to run this code during the lecture. And in that case, we would typically collect the data. We would split it in test and train, as we always do. And here we're just setting up the digits, which are these handwritten numbers. And in this case, these are 8x8 pixel images. So the resolution is pretty rough. So this is a downscaled version of the MNIST data. The full data set is a 28 times 28, and I think it has something like 70,000 images or something like that. Then you can import TensorFlow. We do exactly as before, and here I split into train and test, as we would always do. And then if I'm setting up Keras now, I can create a function where I take the input shape, the number of filters, the number of connected neurons, the categories. These are the learning rates, and these are the hyperparameters lambda. And again, here I'm just setting up, in my case, I'm setting up a field for the filter, which is a 3x3. I decide on the number of filters, 10. So I'm making 10 copies of my image. And I have a 3x3 filter. If you look at the data down here, these are training parameters for the stochastic gradient descent. I'm plugging in the input shape. I have the number of connected neurons in my normal neural network. And then I have 10 categories, which are the 10 written numbers. And then I'm just setting up a set of values for these functions here. I'm using a plain stochastic gradient descent without an optimizer like Adam and so on. And the score function, which I'm setting up, is the accuracy. So when it says SGD, it's just a plain stochastic gradient descent with a given learning rate. So the learning rate is not updated. You can replace that with an optimizer like Adam, root mean square propagation, and other ones. Any questions so far? Okay, so we have going to run that one, and then this is my model. I loop over the learning rates and then the hyperparameters. And you can just let this run, and you will see it will take some time. Oops, I think I didn't run everything here. What is complaining here now? It ran before I had my lecture here, so
Okay, let's just leave it, and I will try to fix it during the break. It actually ran before the. I must have done something here, which I. Yeah. Okay. Let's just leave it here because it should run actually. It's not so important to actually run this code. You can do a similar thing with PyTorch. And in PyTorch, in this specific case, I can now set up 2 convolutional layers. I use max pooling. And then there's something which I wanted to mention, which is called dropout, which is an additional parameter which we can tune in the calculations. Dropout means that not all neurons are connected. And then in this case, I have 2 fully connected layers. And with PyTorch, I would then set up, I load in the data, the MNIST data set here. I'm setting up my convolutional layer. So in this case, I have a 3x3 layer. I make 64 replicas. I have padding equal to 1. The pooling is a 2x2 pooling. And this is my linear neural network. So this is a plain neural network. And then it takes in the final layer here, which now contains only 10 output nodes. And then there's a feed forward part. And this is just my final neural network here. And then I just call the CNN. I use the cross entropy. And in this case, I can set up the Adam optimizer. And here I'm running it for only 1 learning rate. So if you have understood the basic philosophy and you see in the way it's set up with TensorFlow, it's not that difficult to see how you can set it up with PyTorch. And in this textbook by Rashka, you will find many, many examples on how you can do that. But I wanted to say, instead of running this, I just wanted to say something about dropout. This is also a regularization technique, which many tend to use. And it's used to prevent overfitting in neural networks. And during training, then I randomly selected typically 20 to 50% of the neurons in each layer. They are deactivated. So you will typically just pick them randomly. And this compels the network to distribute feature representations across multiple neurons instead of relying on a small subset. And there is a random neuron deactivation. Neurons are randomly ignored during each forward pass. Then it normally allows you, or it's supposed to reduce overfitting. And at test time, all neurons active with weights scaled down to account for the training phase dropout. And dropout is normally applied after fully connected layers in CNNs, but they can also be put in the convolutional layers, but it's pretty common to do that in the neural network part. And you can actually apply this technique in a standard neural network as well. So instead of you having 100 neurons in each hidden layer, you could now say that I'm only going to keep randomly in the feed forward pass only 50 of them instead of the 100. And you would select them randomly. So it's a way to reduce both the dimensionality and it can help in reducing overfitting. But so that it doesn't come as a surprise, I mean, dropout becomes one of these parameters which are used in the calculations. And if you go into the manual for either TensorFlow or PyTorch, you will see how you could use that option. And in this case here, dropout is actually something you would put in here. And you set dropout to be 50% here. So that's a parameter which you set. And it's only used normally in the feed forward part. Okay, so this was about dropout. Now, one of the things which I wanted to show you now, because some of you would like to build your own CNN. So the examples which we saw now are more the kind of examples where you understand what goes in and where we have an overarching view on what is happening without us having written a code for it. Okay? So now the question is, how do we do it ourselves? Now, if you look back to some of the codes we discussed 3 weeks ago, when we looked at neural networks, you will see many of the same things popping up here. So if you want to write your own CNN as a project, and this would typically be a full semester project, then you can use this example here as a kind of a way to get started. So this set of functions here, they were actually the codes here were developed by Eric Reber and Gregor, and they were actually following this course in 23, and they wanted to write their own CNN. So essentially what you see here is the output of their project. It doesn't mean that you will write a code like they did, but it can serve as an example. So the code here implements a 2D layer for black and white figures. It has a pooling layer, it has a convolutional layer, it has the flattened layer, and then there's a fully connected neural network, as we have been discussing. So if you now keep in mind this overarching structure, which you have with Keras or PyTorch, now we are going to look at how we can write it ourselves. So I will not go into all the details of the code, because if you want to understand it properly, you have to look at it yourself. But hopefully this can show you how you would structure the code. So you would have the so-called schedulers, which we defined as the ways to change the learning rate. So this is an important part where you now can use a constant learning rate. You can use momentum update. You can use ADA-grad. You can use ADA-grad with momentum. You have the possibility of having root mean square propagation and also ADAM. So these are the ways you can use to update the learning rate. Now, these would be the same functions which you would have in a standard feed-forward neural network. So this class, which you see, is something which you can reuse in a standard neural network, and also when you write your own recurrent neural network code. So this is something you would need to have, irrespective of what you end up doing. And these are popular methods which are widely used in the literature. And then you can use the schedulers. So you would simply call them if you're now using momentum. Then you need to feed in the learning rate and also this parameter which is used in order to keep track of the information from the previous update of the parameters. So I like to call momentum nothing but a memory method where you keep information about the previous iteration. And ADAM, you would use it now with these parameters, which have been fine-tuned by Kingma, who developed this ADAM optimizer. And as I mentioned, this is one of the more popular ones, which has more than 200,000 citations in 11 years. So it's an extremely popular method. And when you use it, if you now look at the number of epochs you would use when you set up a stochastic gradient descent, you define your gradient, which in this case is just given by some random values. And the change is now given by the ADAM scheduler update. And then you have the weights. They are now changed in terms of the previous value, which is this one, minus the change, which is your gradient. And then you reset it, and then you can continue. So that you would have before, your weights would look like this, and after they would look like this. So these are just examples on how you would use these functions. Then the next thing you need to define are the cost functions or the loss functions. So this is another class which is of the methods, which is important. And you can have a logistic regression. You can have an ordinary least square, mean square error. So this is what the function here, just a mean squared error. Now let's see, there's a question here from yeah, this is correct actually. So the values which are plugged in there are actually the default values which have been recommended by people like Kingma and other ones when you use the ADAM optimizer. So that's correct. So the values which you see here are nothing but the standard values which are recommended by the people who have developed the algorithm. Whereas on the momentum method, you can actually change this one. So this is not normally the optimal one. but this means that you would give a weight to the new value of 0.9 and the old value of 0.1. So you keep some memory of the previous iteration. And this is often used in order to reduce gradients which may change from one iteration to the next one, so that you can dampen large variations in the gradients in the iterative update of the parameters. So you have the different cost functions. And again, you can use these cost functions. It also calculates the derivatives by using automatic differentiation. So this is something you can decide whether you want to use JAX. So AutoGrad has now been incorporated into JAX. And AutoGrad as a library is there, but it is not updated with new changes. So JAX is the library which has replaced AutoGrad. And that contains also just-in-time compilation and efficient vectorization, etc., of Python code. But this tells you how you can actually calculate the derivatives of these activation functions. And before we look at the layers that make up a neural network, you also need to define the activation functions. And typically those which you will encounter are things like you can have the identity if you want to. This is often used if you're dealing with a regression problem where you want to fit a function, because then the output from the last layer is normally just the output itself. So that means you just call this linear. So you just spit out the last value which you have. So there's no activation function. Then we have the standard sigmoid. There's the softmax function. We have a ReLO. We have a leaky ReLO. And you can keep adding activation functions. So this is just to give you a certain set of examples. Sometimes it's easier to actually hardcode the derivatives than to call automatic differentiation. Essentially because automatic differentiation uses the chain rule on elementary functions, and using the chain rule on elementary functions means some floating point operations. Whereas if you have simple functions like those which we put up here, you can then just hardcode the derivatives. So in this case, like if you have ReLO, you define the derivatives here, and you have a very simple expression for the derivatives. And here you have examples on how to use the activation functions. And you can see the output from the sigmoid activation functions, and then you can take the derivative of that function. So this is just the input, as we have here, and then you have the output, and then the value of the derivative. And you can then see these examples on how we use now. So this derivative is actually a functionality you have with the JAX or AutoGrad. Now, the next step we need to set up now is actually the mathematics of convolution. And the code which follows now implements this. So convolution, as we discussed, when you have a continuous function, and now we are just dealing with one variable here, this is now given by this integral. And what it means is that suppose now you make some measurements of this f function, and then some of the measurements you want to filter them away. So that means for a time from tau to t, you're now filtering away some of the information. And that is now represented by the mathematical definition of convolution, which is simply this operation which you see here. And last week we went through several examples. And one of the examples we spent some time on was this a simple polynomial multiplication. So this would be a one-dimensional object. And then when we move to 2 dimensions, the typical way you would do this, where f is now your data and g could be your filter. And this is simply represented by this operation here. There should be an equality sign here. I see that. That's a small typo. So here there should be an equality sign, as you can see. I didn't see that before now. Sometimes you don't see the typo before you look at the equations. But suppose now that you have a 2-dimensional object you want to convolute. So suppose this image is a 6x6 matrix, and it just contains this number. And then you have a kernel, which is a low-pass filter. which then could be this filter here. And then when you do the convolutional process, when we are setting it up, so every little cell, so this would be correspond to the first cell. When you do the convolution of this object, you end up with this object here. So that's the convolution you have done. And in this specific case, with stride equal to 1, and there is no padding on this matrix which you started with, you see that we reduce it from a 6 by 6 down to a 3 by 3 matrix. And then clearly you can introduce more and more filters, and you can make many replicas of that image. This is the kind of image which then will be passed to a pooling stage. So in a pooling stage, you could now say that you do a 2 by 2 pooling, and that means that you would pick this block, and if you do max pooling for this block, then the output will be 6.67. In this block here would be 7, here would be 5.78, and here would also have 5.78. So with pooling, you could reduce this one to a 2 by 2 matrix afterwards, if you have a 2 by 2 pooling operation. Now, so what you see is the result is smaller in shape than the original image or the original matrix. And this occurs when using convolution without first padding the image. So we didn't have any padding here. And this is something you could decide to do, because if you do padding, you will actually increase the size of this matrix. So how many rows and columns you wish to pad the image with depends strictly on the shape of the kernel. So the kernel is the filter. And you can actually, you're not limited to have a kernel or filter which is quadratic. You can have a rectangular one. And in that case, you can actually decide whether you want to, how many rows to pad the image. If you want to do a padding here, you can pad the image with R additional rows and C additional columns. And there's a simple recipe for doing that. So if you do a padding, this is what you could have. A typical example. And as we mentioned last time, one of the reasons why you do that is that when you perform this filtering, is that the corner values appear normally in only one of the blocks of the matrix, which is downsized. So let me see here. We have a question online. Yeah, you can. I'm not so sure if you can input. I think you can input a custom activation function in PyTorch. I haven't done it myself, but I think you can do that. I haven't done it, but I would be surprised if you could not do that. Okay, so the code which comes in here does the padding for you, and it also performs a convolution here of the matrix. So this is essentially just a mathematical operational convolution, which we have implemented here. So in a certain sense, when you look at these codes, I mean, in the lecture here, we're not going to go through what this actually means, because this is just you implementing the mathematics of convolution. And it's not so exciting to go step by step, because the process itself is now represented by us taking, for example, this example here. So what we are doing now is simply to implement the code which you see, or the formula which is given here. And that's what is implemented down here. We do a padding of the matrix. We can increase the size with zeros, and you define how many of these you want. And then you have the convolution itself here. So these are just the basic steps here. Should we take a small break? Is that okay? And then after the break, we are going to look at types of outputs so that you get some familiarity with the basic building blocks of a convolutional neural network.
So welcome back. And what we did before the break was to look at how we can build our own convolutional neural network code. So as I said, as a kind of warning, don't get, let's say, upset by looking at all these codes. I want to guide you through and show you how you can encode the different elements and how you would do that. what most of you will end up doing, unless you want to write your own code, which has been a typical path in the course here, is to use either TensorFlow with Keras or PyTorch. This is the most common approach which everybody takes. And these two libraries have an immense amount of flexibility. So there's a lot of options you can use, tons of activation functions, etc., etc. But hopefully by doing this, we can demystify many of the operations which we have with the neural network and convolutional neural networks. So before the break, we discussed this padding, and the code which follows here is an example on how you can use padding and implement that. And then we also had the basic convolution operation, which comes in here. And we can then, when we want to use this, we can then just return a convolution image. And in this specific case, we are just setting up an image which now returns, it has stride equal to 1. This is the way we would use it. And that has an original image of shape 6 by 6, and it ends up with an image which is 6 by 6. We can continue and then generate further features. So if you now look at the CNN, the values of the different kernels are normally randomly initialized. So these are parameters which we need to train. And then they are learned during training. And these kernels will then extract information regarding the pictures, such as, for example, the edge detection filter demonstrated below, right below here. There's actually a demonstration of that. And that extracts the edges which are present in the picture. So you can tune these filters so that you can extract specific features. And this is something which is normally handmade by the users. And in this specific case, there is an image. This is the original image of a dog. In the previous case, you had this image of the square in Volterra. So you can just choose the image you want to and just do the downsizing yourself. So this is the original image. And then you can have a result of convolution with a Gaussian kernel. This is often used. So that blurs the filter. That's a blurring filter normally. And then you can see your downsized image here, which you see is very much blurred. So these are examples of type of filters or kernels. So you will often see the word kernel or filter being used interchangeably. And this would be an example of one of these downscaling. And then there are different types of filters. This is an edge detection filter. And in this specific case, this would not be a very good thing to use because, so this is called a Sobol filter. Actually, if you make a search and look at filters used in CNNs, you will find many different types of examples, which are tailor-made to specific types of problems. So if you have a dog like the first image, which we showed you, to use an edge detection filter is not very meaningful. But if you are looking at houses or pictures of buildings, etc., then it makes sense to have a filter which detects the edges. And you see that very clearly here. So like this image blurring down, it makes sense, whereas this one doesn't make much sense. You still can see something which looks like a dog here. So you can decide on the number of layers. So when you're running these codes, you typically would initialize the global variables for readability. And it's actually useful to organize this before you start. So you define the class of layers, you have a feed forward, you have the back propagation, you're resetting the weights. And these simple examples here, after you've gone through these basic elements and understanding of applying a convolutional network to some spatial data, this is actually spatial data we have, then you can just go into the workings of a convolutional neural network. And this is essentially what follows here. This is the basic structure of a convolutional neural network and the training itself. So I'm not going to go through all the details here. I'm going to leave this to you to take a look at. But this just repeats many of the topics which we discussed before. So we have a feed-forward part, as we will always have. And we will then do the convolution with a given kernel, as you can see here. And you would have the backpropagation part. And in the backpropagation part, you would then train the different parameters. So I'm just going to scroll quickly through that because there's a lot of stuff here. You have the padding itself. You will also find the max pooling, which comes in, resetting the weights, etc. So then the next part is actually the backpropagation in a convolutional layer, which is actually discussed down here. So I'm just going to run through this. So when you do a result of this convolutional layer, this is the image which you have downscaled and which you then will train in a standard feed-forward neural network. So the pooling layer is something you would also need to implement. So the first part here, which you saw, was without the pooling layer. And then you would need to define the pooling layer. And this is the way you would actually include it, just as an example. And you need to also take into account topics like stride, the padding, etc. You can then decide whether you want to do max pooling or you want to do the average one. And you can see that quickly here. This is NP max. And then you have a mean value. And then you would go through and scale down the image. And here you have the backpropagation, which is also included. So this will be a convolutional neural network with the pooling. Then the next step you need to add is the flattening. So this takes the image. So the first cases we've seen is us going through the image with just the convolutional part and scaling it down. Then you need to add the pooling part. And then comes the flattening layer, which comes in here. And the flattening itself moves into a fully connected neural network. And here you will see again the standard things like a feed-forward part in a standard neural network and a backpropagation part in the standard neural network. And you can decide how many layers you want to have in the neural network. And here you have the standard gradient updates. You decide what kind of gradient update you want to do, etc., etc. So you see gradually how you can implement the elements. So we've gone through the convolution stage itself. And it's actually useful to do that, just to look at what convolution is doing with the image. And then when you've done that, you can use pooling and scale down the image further. That was that functional pooling. And then the next step is to flatten it. So you can feed it into a standard feed-forward neural network, which is this final stage, which you have here. And that is essentially the setup of a convolutional neural network with the codes you need. And you can see here you have an output layer, and then you define what kind of cost function you want to do, etc., etc. So I'm just going to quickly go through that. And there are also discussions about the optimizing the convolutional layer. I will not discuss that in any detail. I just leave that to you guys, so I don't keep on boring you with all these kind of small details, because when you go into every field into machine learning, there is always a discussion on how do we optimize this in the most efficient way. Then, so I'm just going to skip many of these discussions because it's not so exciting in actually going through all the details. But what you will find here is the final code for the CNN, which now includes all the layers and allows for training on image data. So this is just the fully convolutional layer with pooling, with flattening, with a standard feed-forward neural network, etc. So this just collects everything which you've seen here before. You can see that you have a flattened layer, your convolution layer, and the pooling layer here. And then at the end, you compute the scores and make predictions, you calculate the accuracy, etc., etc. So the usage of the code, you need to specify the kind of scheduler you want to do. You specify the type of classification problem you want to do. This is just a seed which you give to the network. And then you decide what kind of cost function or loss function you want to optimize in the calculations. And then if you note that the CNN object, you can begin to add layers to it. And many of the add layer functions have default values. For example, add convolutional layer has default vstride, which is set to 1 for the vertical one and for the horizontal one. And if you have a square matrix, which is fed in, the default value here is just 1. So you can see typically a standard setup here. You have a kernel of height 3, width 3. You have an activation function, which is a leaky reload. Input channels, just 1. You have the flattened layer, the fully connected layer, and here's another fully connected layer which you can set up, and then you have an output layer. So in this case here, after you've done the convolutional part, so there's just one convolution stage, you flatten it, and then you run through one fully connected layer with 30 nodes with LRELO as activation function. You do another fully connected layer with 20 nodes, and then you have a final output layer with 20 nodes, and then the softmax activation function. So this would be a typical setup here. So here what we've done is to create a layer with one input channel with a kernel height of 2 and a width of 2. So it's a 2x2 filter. It uses the ReLO function. And then the layer outputs a one feature map, which is then fed into the subsequent layer, which is a flattened one, a hidden layer with 30 nodes, a hidden layer with 20, and then the final output layer. So this mimics, in a way, the way of thinking. So if you look at this function here, this one, after all this coding, so you can see the codes are actually the gritty-nitty detail of what TensorFlow and PyTorch are doing for you. But this essentially, if you look at this block here, that mimics what you have seen before in the beginning of the previous lecture with TensorFlow and Keras and PyTorch. That sound okay? And then you can encode the data. If you use the MNIST data and you have 10,028 times 28 images, this is the way you would prepare the data for the calculations here. This is your score function with a CNN fit. And you have a lambda parameter of 10 to the minus 5. You do 10 batches. You have 100 epochs. And this is your final calculations here. And a typical example here on this MNIST data is in your training here, you're getting a fit close to 1, an accuracy score close to 1. And this is the validation part, which is creeping towards 98%. And in this case, this is actually a very simple training model with only 100 epochs. So it's a very short calculation. And the thing which you will see when you're running this type of calculations is that sometimes you go crazy because there are so many parameters to tune. And you need to set up a strategy for which parameters you want to tune first. And the typical parameters, again, the most sensitive ones are the learning rate and this hyperparameter lambda. But then you need to play around with different filters and different pooling strategies. And you can also play around in the architecture with different types of activation functions. So these become parameters which you will tune in the calculations and applications of a specific architecture to your data. So in this specific case, we got a result, which was 98% roughly of an accuracy when we trained this with 100 epochs, which is normally a pretty small number. And the reason why I have these small numbers is simply because this is something I could run before the lecture started without having you to wait till the results ended, because then there's always a risk that I will come with some of my lame jokes. Okay. And the scheduler here is what you typically could use as Adam. You set up the CNN, you set up the convolutional layers, you set up the pooling layers, and then you have a new pooling layer. You have a convolutional layer with the different channels you want to have, etc. So this is just another way of just setting up your network by setting up the different layers with different poolings. And then, so here you can set up an asymmetrical one-dimensional kernel. such that you have a 7x1 kernel in the first convolutional layer, both max and average pooling. You have an asymmetric stride in the unoptimized convolutional filter. You have more pooling, then you have a flat layer, and then a hidden layer with 100 nodes, which you have here. Using El Relo, another hidden layer with 10 nodes, and then that uses a sigmoid. And then finally, here you have 101 nodes, and then you just have the identity. So these are just examples of what you can do. Okay, so I'm just going to skip some of these things because there are many more technicalities which you can dive into. One thing which is widely used is what is called Fourier series. And this has been used quite a lot in imaging. So if you're interested in that as a kind of filter, there are actually filters which use the Fourier series, and this is something you can implement if you want to. Now, for our dog, this is not very optimal because there are features there which are lost. But if you have data which can be well described in terms of a Fourier analysis as filter, then you could use that actually. So this ends the discussions about recurrent neural networks. No, sorry, convolutional neural networks. And today we actually have an additional presentation of a project which deals with a physics-informed neural network. And instead of having the presentation after the break, I thought we could have it now. So I'm going to stop my lecture here. So I will stop the recording of the lecture. And then Bjørn Egil, who has a project on physics-informed neural network, will make a short presentation, if that's okay with everybody. Because I know that many of you have to, are following another course, so you have to leave after the break rather quickly. So I'm going to stop the recording here. And so let's do that. And then next week, we begin with recurrent neural networks, which is a new type of neural networks.